Hello students, subscribers, and viewers. Here is another problem on finding beam deflections by the matrix approach. So by matrix approach, determine the nodal displacements at A, B, C, and D. The moment of inertia of AB is equal to that of CD, while I of moment of inertia of portion BC is 2IE is constant. So since the calculator is only capable of solving four simultaneous equations, for our solution 1, we consider ABC first. So because we consider ABC, we imagine that AB is A and B are fixed. So therefore, this 20 kilonewton load will have no fixed moments to produce. So the load is negative 20, 0 moment. For BC, the fixed moment is counterclockwise here, W28 square over 12, and that is 320 over 3 counterclockwise here, same 320 over 3 counterclockwise. The upward forces, fixed forces, are not computed because anyway they will be transmitted to these supports, and the expected deflections would be 0. So since we only consider ABC, CD is treated as an overhang and not as fixed-ended. So the moment produced by this load on this overhang is counterclockwise, and it is 20 times 2 times 1, so it is 40 counterclockwise as shown. So therefore, the nodal forces at A would be negative 20, moment 0. At B, opposite to this, so negative 320 over 3, or clockwise moment, 320 over 3. Here, 320 over 3 minus 40, and that is 200 over 3 counterclockwise, because the net fixed moment is 200 over 3 clockwise. So anyway, let's set up for the stiffness of member AB, 12 EI over L cube, so 12 times 1 over 2 cube. So this would be the stiffness, 6 EI over L square, the negative of this, and we just copied that. So I will not explain further the setting up or filling up of this stiffness of member AB and the value, because as a student in matrix structural analysis, you should know how to fill in these cells. And the numbering is 1, 2, 3, 4 for AB. Next, for BC, remember that moment of inertia is 2, so 12 times 2 over 8 cube. So for BC, this will be the stiffnesses, and it is marked 3, 4, 5, 6. Finally, later in our second solution, we have to consider CD, which is equal to AB, and the numbering only differs because this is 5, 6, 7, 8. So that would be later. So therefore, as mentioned earlier, the load at A would be negative 20 and 0. At B, negative 320 over 3, opposite to that. And at C, or node 6, 320 over 3 minus 40, and that is 200 over 3. So negative 20, 0, opposite of 320 over 3, so clockwise and clockwise moment is negative. And here 320 over 3 minus 40 is the net fixed moment is 200 over 3 clockwise, so the nodal load is opposite counterclockwise, so positive 200 over 3. So 1, 1, cell 1, 1 is 1.5. So we only consider A, B, and BC, remember. 1, 2 is 1.5 also. 1, 4, 1, 4 is 1.5, and 1, 6, there's no 1, 6, so 0. Then we copy 1.5, 1.5, and 0. 2, 2, 2, 2 is 2, 2, 4, 24 is 1, and 26 there's none, so 0. Then copy 1, 0. 44, 44 there's 2 here, and 1, 2 plus 1 is 3. 46, 46 is 1 half, so we copy 1 half also. Then finally 66, 66 is 1. So from here we can now solve U1, U2, U4, U6, which corresponds to delta A, theta B, and theta C respectively as the product of the inverse of this matrix and this force matrix here. So with your calculator, we can now compute these displacements equal to these values. Then finally, we consider CD this time as fixed and dead beam. Then these are the moments. W22 square over 12 is 20 over 3, and the upward force, upward reaction, especially at D, is 20 times 2 over 2, so 20 upward as shown. So don't mind the forces at C because we have found the displacement 0, delta C, and theta C is 400 over 3. At D, opposite of 20 is negative 20, and opposite of this clockwise moment is counterclockwise moment 20 over 3. So we have F5, F6, F7, F8. As I said, at 7, opposite of upward 20 is downward 20, negative 20, and opposite of this clockwise moment is counterclockwise moment 20 over 3. So we just call the forces at 5 and 6 as F5 and F6, and this is the stiffness of CD. We just copy 5, 6, 7, 8. Remember that delta 5, delta C is 0. Then this is theta C, 400 over 3 from the preceding calculations. Then unknowns U7 and U8, which corresponds to delta D and theta D respectively. So by expansion, especially these last two rows, negative 20 plus 1.5 times 0 is still negative 20. Then negative 20 minus quantity negative 1.5 times 400 over 3, that becomes plus 200, so 180, and 20 over 3 minus 400 over 3 is negative 380 over 3. So the forces would change to 180 and negative 380 over 3. Again, 180 is negative 20 minus negative 1.5 times 400 over 3, and negative 380 over 3 is 20 over 3, 1 minus 1.5 times 0, then minus 400 over 3 is negative 380 over 3 equals EI. Then copy this 2 by 2 matrix times U7, U8. From here, U7, U8 can now be solved as the product of the inverse of this matrix and this force matrix here. So U7, U8, which corresponds to delta D and theta D, is equal to 680 over 3 EI, and theta D 320 over 3 EI. So that's it for the first solution. For the second solution, we consider BCD this time, and therefore the effect of the 20 kilonewton load will be as shown. So this is an overhang. The moment produced by 20 is clockwise moment, which opposes this 20 times 2, so this is 40 clockwise. And the fixed moments here would be the same, 320 over 3, because this is treated as fixed and dead. CD is also treated as fixed and dead. So 320 over 3, the upward forces are, don't mind, because these are supports. Since CD is considered fixed and dead, then we just grab these values of moments and upward forces. So therefore, the net moment at B is 40 minus 320 over 3, and that's negative, so that means it is counterclockwise because the net moment there is counterclockwise, so the nodal load is counterclockwise at 4. So that would be 200, negative 200 over 3, 40 minus 320 over 3. Then here, 320 over 3 minus 20 over 3 is 300 over 3 or 100. Then here we have opposite of 20, negative 20, and opposite of clockwise moment is positive counterclockwise moment, so 20 over 3. So opposite of 20 is negative 20, and opposite of 20 over 3 clockwise is counterclockwise, positive 20 over 3. Then we have numbering 4, 6, 7, 8. So this corresponds to theta B, theta C, delta D, and theta D. Then 4, 4. So take note, we consider BC and CD. So 4, 4, we have 1 here, 1, 4, 6, 1 half, 4, 7, none, so 0, 4, 8, 0. So copy 1 half, 0, and 0. This is 6, 6, 6, 6, 1, and 2. So that's why we have 3. 6, 7, 6, 7, negative 1.5, 6, 8 is 1. Then we copy negative 1.5 and 1. 7, 7, we have 1.5, 7, 8, negative 1.5, copy negative 1.5, 8, 8 is 2. So this is now the structural stiffness matrix, and we can now compute U4, U6, U7, U8 as the inverse of this matrix times this matrix here. So U4, U6, U7, U8, which corresponds to these displacements in particular, would be equal to same U4, negative 400 over 3EI, U6, positive 400 over 3EI, U7, which is delta D, 680 over 3EI, and U8, which is theta D, 320 over 3EI. Then we consider AB. So since it is now treated as fixed-ended, then the load is negative 20. There's no moment produced if we imagine this is fixed at A, fixed at B. So only negative 20 opposite to this reaction here. So downward negative 20, 0. Then F3, F4, don't mind. Anyway, we know that delta B is 0 and theta B is U4, negative 400 over 3. So we have unknown U1, U2, delta B 0, and theta B negative 400 over 3EI. Then this is the stiffness of structural system stiffness of AB. Just grab it here. Then we expand. So negative 20, 0 is equal to this matrix times U1, U2 plus this matrix times this known displacement matrix. So negative 20 plus minus negative 1.5 times 0 plus minus 1.5 of negative 400 over 3. So that would become 180. Then 0 minus negative 1.5 times 0. Then minus 1 times negative 400 over 3 is positive 400 over 3. Then equals EI. Then we copy this matrix here, 2 by 2 matrix times U1, U2. So U1, U2 is the inverse of this 2 by 2 matrix times this force matrix here. So U1, U2 can now be solved using your calculator, and that corresponds to delta A and theta A. And it should be equal to the same values here, 640 over 3EI and negative 280 over 3ai. So that's it for this sample problem video. I hope that you were able to understand, follow the explanations and the solutions.